This is problem 7. This is a balancing chemical equation problem. And the thing about balancing equations is essentially we don't want to offend the element rights activists. No element can be created or destroyed in any reaction. The elements are the things that are indivisible by any chemical reaction. So, in other words, there has to be the same amount of every element on the left-hand side as the right-hand side. And this is what we're going to balance. And we're going to find there's a couple of categories of reaction here. The first one is going to sort of fall in the category of it's more of a molecular reaction. There's going to be a couple of ionic reactions here that there's going to be some tricks with that will make it easier. But in this case, we don't have any such tricks available. So we just have to start with any element and go from there. I recommend starting with everything but oxygen. And in this case, iron. There are 2 irons on the left-hand side. There's 1 iron on the right. So I can easily fix that. Now we cannot adjust the stoichiometric, the formula subscripts. We can adjust only the stoichiometric coefficients. And so I can balance the iron by putting a 2 here. Now we've balanced the iron. That may have to change later on, but for now, we've balanced the iron. Now I'm going to go balance the aluminum. I have 2 aluminums on the right. I have 1 aluminum on the left. So now I will balance aluminum, placing a 2 there. Now I'm going to go to the oxygen. We'll balance the oxygen last. And I've got 3 oxygens on the left. I've got 3 oxygens on the right. We're done. And so there is no set pattern, but I advise with problems like this that you follow that sort of a sequence. Do the oxygen last. And now that is distinct from problem B. This is an ionic compound. This is ammonium carbonate and silver nitrate. And now there are 2 different types of ionic compounds. But the thing you want to notice, and the feature that's going to give you the best advantage here, is note that these are molecular ions. This is an ammonium ion and a carbonate ion. This is a silver plus 1 ion and a nitrate ion. The ammonium, the molecular ions, are the same on the left as the right. In other words, it's ammonium here, it's NH4 here as well. It's a nitrate here, NO3, it's NO3 here. So we will not have to adjust within those. We will keep them, we'll balance them as whole molecular ions. And we have a carbonate on the left, it's a carbonate on the right. There are no bonds broken or made. We're just simply going to be changing partners. Okay? And so I've got 2 ammoniums on the left. I've got 1 ammonium on the right. So I'm going to balance the ammonium first by placing a 2 in front of the ammonium nitrate. Now I've got 2 nitrates on the right and 1 nitrate on the left. So I will place a 2 in front of the silver nitrate, and now I've balanced the nitrate. So the ammonium is balanced and the nitrate is balanced. Now let's talk about carbonate. I've got 1 carbonate on the left, I've got 1 carbonate on the right. So the carbonate's balanced. Now we just want to balance the silver. I've got 2 silvers on the left, I've got 2 silvers on the right. We are now balanced. So it's just going through that simple iterative process back and forth, but recognition of the molecular ions is going to simplify this process a great deal. So we're going to do that again with problem C. Here I've got phosphoric acid and calcium nitrate. So I've got phosphate ion and 3 hydrogen ions calcium ion and 2 nitrate ions. Here I've got calcium phosphate, which is 3 calcium ions, and 2 phosphate ions, and nitric acid, which is, or hydrogen nitrate in this case, because it's not in water. So I've got a nitrate ion on the right and a hydrogen ion on the right. So we can focus on, again, balancing the molecular ions. Well, I've got 1 phosphate on the left, and I have 2 phosphates on the right. So I will balance that by placing a 2 here. And now that stoichiometric coefficient is going to say I've got 2 phosphates on the left, 2 phosphates on the right. I've got 2 times 3, which is 6 hydrogens on the left, hydrogen ions, and I've got 1 hydrogen ion on the right. So now I'll place a 6 in front of the hydrogen. And now I've got 6 hydrogen nitrates, and I've got 6 hydrogen ions here. Now, how many nitrate ions do I have on the left? I've got 2 on the left. I've got 1 on the right. I've got 6 on the right. So that's easy enough. I have 6 on the right. I've got 2 on the left. What do I multiply 2 by to get 6? I'll put a 3 here. And now I've balanced my nitrates. 6 nitrates on the left, 6 nitrates on the right. Now we have to balance the calcium. I've got 3 calciums on the left. I've got 3 calciums on the right. We're done. So if we recognize the molecular ions are intact for the entire process, it brings great simplification to balancing particular ionic reactions. They turn out to be the easiest. It would have been a whole different thing if we had counted oxygens. We'd have gotten very quickly confused. Whereas up here, we had to. We had to deal with the oxygen because oxygen bonds were made and broken. And this is going to be true with glass. This is another molecular reaction. This is a combustion reaction. And so this is going to be balanced in the following fashion. With these, the trick is I'm going to balance the carbon first, the hydrogen second, and the oxygen third. So that's consistent with the little theme we had up top. We'll do the oxygen last. Now, the carbon, I've got 3 carbons on the left. I've got 2 carbon dioxides on the right. So I'll balance that this way. And now I've got 3 carbons on the left, 3 carbons on the right. Now, I'm going to balance the hydrogen. The hydrogen, I've got 8 hydrogens on the left, I've got 2 hydrogens on the right. So I'll try a 4 stoichiometric coefficient in front of the water and see where that takes me. Now I'm going to count oxygens. I've got, and I'm going to count them in terms of O2s. I've got 3 O2s here. I've got 4 oxygens here, which is 2 times O2. So 2 O2s and 3 O2s is 5 O2s. And so now, does it balance? I've got 5 times 2 is 10 oxygens, 3 times 2 is 6, and 4 is 10. So we've balanced oxygen, we've balanced hydrogen, and we've balanced carbon. And that finishes that.